So the chart on the right there is a from the top azimuth pattern of a long wire. This 0 dB line out here is equivalent to 11.23 dBi, and then as you go down, you subtract from that. So this -10 line would be about 1 dBi, or pretty much no gain. Even though it is directional, and even though you have less gain over here, you do still have signal exiting even at the -30 dB point. If we do the math on 100 watts, we divide by 10 twice, so you end up with 1 watt if you were transmitting 100 EIRP out this direction. That math doesn't necessarily have to make sense as long as you understand that the stronger part of the signal is here and the weaker parts are over here. This is VOACAP online. I prefer it to the installed VOACAP. I think it's easier to read, but to give you the quick map on it, time on the outside and UTC, and then wavelength on the vertical. Red is good, green is bad. I don't know why they made it like that. If you were to find the maximum usable frequency off this graph, you would essentially follow the line that's white and colored, and then you would end up with the maximum usable frequency the same way you find it on the downloaded software. So the first antenna here was that 286-foot loop. It's a full wave at 80 meters if you're not as fast at math. And this is the one that came directly from Chameleon. I believe it's like $250 if you buy it from them. It's a ballon and a bunch of wire. It's not the hardest thing in the world to make. But you can see across the HF spectrum here, you end up with a VISWAR generally in the model below 5:1, which is pretty good. If you strap your nano VNA to that antenna and pull the SWR off of it after you've actually constructed it, this is what you end up with. And in the real world, the VISWAR was less. I did test the coax. The coax was fine. So the real antenna showed a lower VISWAR than the model ended up showing. Really under 3:1 for the entire spectrum, which is pretty good. When you look at the gain for this antenna, this was modeled 30 feet over the ground. I don't think I wrote that anywhere. So this is when you feed it at 7.15 megahertz, and all the frequencies in here are in the ham band, just because that was what was easy for me to think about, but it applies outside as well. And if you do want to run these EasyNAC models, those are in the same place on GitHub as this actual presentation. But you can see the main lobe of elevation comes off at about 50 degrees, still 7.4 dBi. So what this tells me is I'm going to get some pretty good closer propagation. I'll call that not quite NVIS, but 250 to 600 miles is probably what I'm looking at here. So this is how I got my close-in, everyone that was within the Georgia, Florida area was off this loop. We showed on the other slides, if I feed the same antenna at the same height at different frequencies, the main lobe of my radiation decreases as my frequency goes higher because the wavelength is smaller, so I'm therefore higher off the ground versus the wavelength than I was before. So this is the same exact antenna fed at 21 megahertz instead of at 7 megahertz. My angle of radiation, came down to 20 degrees. My gain went up to 12 dBi essentially. So the same antenna was versatile versus if I was trying to use my inverted V again, my end-fed half wave that may not have a low VISWAR, where I could use it both for long distance and short distance on the same exact antenna. That was a super useful feature, and we actually did it. So this was at 1330 Zulu in Florida, would have been -4. 13 minus 4, 9. Public math, probably 9:30 in the morning. So still pretty early as far as HF is concerned. But when we were actually using it, you can see these purple balloons here are 7 megahertz. The orange or the orange gold ones are 14 megahertz. The yellower ones are 18. The brown ones are 21. And you can see that the 21 megahertz goes a lot further than the 7 megahertz. And even though, well, actually, it's kind of tied into the maximum usable frequency. But this really has to do with the takeoff angle from that antenna that we were modeling before. So it's not just an EasyNAC thing that tells you that, yeah, it's going to come off at 20 degrees. You can actually demonstrate it to yourself in real life. And this was also a really helpful teaching tool for the soldiers when we were setting this up. So this next one, if you look back at the previous slide, the highest frequency that we had before to California was between 18 and 21 megahertz. If we went back and looked at the VOACAP model for that day with all the data, we end up with the same results. So not only a good tool to test your antennas, but a good teaching tool for all the soldiers out there. Yeah, I like Whisper. I don't like it for this. I'm trying to get back to where I can see you. That didn't go well. But I don't like it for this because FT8 itself is cheating. I can hear FT8 at -24 SNR. I can hear whisper way below that. I don't know the number. When I'm doing ME6 or even LDV, the number goes up to LDV is like -10, I think is the best you can do for SNR. And then ME6 is above that. So whisper is great for testing propagation. I don't like it necessarily for testing these antennas, if that makes sense. So this is the model of the 500-foot loop. It looks a little different than the one before. This is the actual VISWAR measured with the nano VNA. And the nano VNA only samples 100 places on the spectrum that you give it. So if you really look closely at this, you can see it's two separate pictures. We did the lower half of HF and the upper half in two separate sweeps just to get a little bit more granularity in the results. But what we see is very similar to the 280-foot loop, where you have low VISWAR across the majority of the spectrum, and even some points all the way down at 1. These loops are in a triangle. The shape isn't super significant. I know, Cody, you discovered loops probably about the same time I did, but as you want the perfect shape for a loop is a circle. It encompasses the most area inside the loop. The second most perfect shape is a square. The third most perfect shape is a triangle. So generally, a triangle is the easiest to build because you need the least amount of supports. Things start to get weird when you make the antenna weird sizes or weird shapes. If you look on the bottom right here, you can see that it is a triangle, but it's nearly a right triangle. And the gain pattern gets funny. You get less gain. This is 6 dBi. I believe the last one was 7 at the same frequency. And you just end up with weird results is the bottom line here. It did still end up being oddly directional, one frequency, but as much as you can, key between these two is to keep it close to this perfect triangle there. Same thing generally, different frequencies get you different places in the US, but we ended up with 4 long wires. They each covered about 30 degrees of beam width azimuthally, and 2 loops. This loop was that one that was weird shaped. This one is it was perfectly shaped when it was out there. I can't draw so well in Google Earth. And this was what the long wires were actually doing. So the easiest way to read this is to look at the arrows at the top here. So each of these arrows was a 500-foot-ish wire. One of them was closer to 380. And when you model that in EasyNet, you get about a 30-degree beam width. So we figured if we took 4 of them and covered 120 degrees, we could get most of the US. One thing you notice, and it'll come up, is they also work in the opposite direction if you don't terminate them with a resistor. So this is also marginally useful for the South America stations for Noble Skywave. For QRPX, it wouldn't have been. And then I didn't put this disclaimer at the beginning, but this strategy itself only works really well if you're in a corner of the US. So it just so happens that New York is basically in a corner of the US. Fort Irwin is on a side, kind of a corner. But if you happen to be in Kansas, like Rob is now, it's not going to work as well for you. You need a lot more antennas. All right, so 4 long wires, about 30 degrees each. We'll cover the long wire once because it doesn't change much. This was the modeled VISWAR, which looks similar to what we had before for a 500-foot antenna. This was the actual result. So the model showed it would get up to a little over 10-to-1. In real life, that didn't happen. I don't know why yet. Coax was still good. But the maximum VISWAR here was about 4-to-1 across the HF spectrum. And then going back to using the same antenna at different frequencies at the same height. So if we look at what we would want for NVIS propagation, which is about 7 megahertz during the day, this is what you would get. 10.17 dBi gain, still really good. And 25 degrees of elevation is just a little low for NVIS, but that'll give you the long distance propagation at night that we were looking for. So while the loop at that height gave us the closer in stations, this gave us the further out stations at night. And then this is where you really start to exhibit gain at kind of narrow beam widths at the higher frequencies. This is a better picture, I think. So this is where we got that 30-degree beam width per long wire, similar gain in the back, still 11.2 dBi, very performant antenna. And then if you do the same modeling, this actually gets at the question about whisper. So these were weak stations on FT8, and these were strong stations. I didn't know at that point you could turn on the received SNRs in this block, but you kind of have to believe it until you go out and do this yourself. These were stronger than these ones, and that's why I don't necessarily like the weaker signal modes. It's just that PSK reporter, the most common one is FT8. Similar thing as we saw before, we went through and modeled what the maximum usable frequency should be. And then went through and did the PSK reporter and found where it actually was, and they did line up pretty well. The rest of this deck is similar. We special ordered some wire from Chameleon. So if you've ever ordered their antennas, they come with really nice, the word on Ham Radio Workbench is supple. 20 gauge wire. And so we reached out at one point and said, hey, can we just get a roll of it? And he was like, yeah, we have 2 different kinds. They had Kevlar and non-Kevlar that don't use 14 gauge. That was a mistake. There was no difference, to be completely honest, if you end up buying this for yourself or GPCing it for a unit. Just buy the non-Kevlar kind. It was pretty strong as it was. Our setup time, I kind of alluded to field day where there's rules for how much time you can use a setup. By the time we set these antennas up, actually did the competition, and then came back the next week to tear down, they could be up for 7 to 10 days in the wind, and that 20 gauge non-Kevlar wire stood up the whole time. So if you do have the funds for it, that's a nice thing to have. All right, we said it also propagates off the back of the antenna in those gain models. So this long wire was pointed kind of up towards the Pacific Northwest, Washington, Oregon, and then also encompassed Montana, Idaho, in that area. But because it has that reverse propagation as well, that was the first time in my life I'd ever hit St. Helena on FT8. So I got another contact there, another one to add to the log. But just to double down on the fact that it does propagate off the back. And this was one time that our model really didn't line up with what we were seeing, which is another thing to underscore in the presentation. So just because the model says it's not going to work, doesn't mean it's not going to work. A lot of the times at QRPX or at Noble Skywave, you'd be on the phone with the guy on the other end, be like, hey, where are you? I want to put you in speed, or I want to put you in vocap to see what's going to work. And they come back and say nothing's going to work. They're going to move on to the next station. I usually try to convince them to give it a shot. Most of the time it works. You know, models are only good as good as the data they're fed, and they don't always have the best data. So only trust them so much. So key takeaways here from this presentation, the second part, is that the same antenna is going to act differently based on what frequency you're giving it. And if you have a longer antenna, you have more harmonics to take advantage of. It's going to act better where you want it to. So I guess what I learned in 3.5 years is use more wire. But it didn't occur to me at the beginning, which I think would be useful to someone that hasn't done it before.